Hello everyone. Today I would like to talk about the sound wave. Sound wave, this is the longitudinal wave. Sound wave is the longitudinal wave, and sound wave needs medium to propagate. This wave, sound wave, it needs the medium to propagate. It cannot pass through the like a vacuum, okay? But the sound wave, it can travel through the air, that is gas, solid, and the liquid. But the speed of the sound wave in three different media, they are different. So the speed of the sound wave, in air is 443 meter per second. This is at 20 degrees Celsius. And the speed of the sound wave in air, again, this is 331 meter per second at 0 degrees Celsius. So the speed of the sound wave, from these two examples you can see that it depends on temperature also. So there is a formula. If you are interested, you can use this formula. The speed of the sound wave, this is in the air, this is equal to 331 plus 0.6 t meter per second. Here this T is temperature in Celsius degree. T, this is temperature in Celsius degree. Temperature in Celsius degree, okay? And in the solid and in the liquid, of course, we can measure the speed of the sound wave, but I don't think you need that here. So simply, if you know the speed of the sound wave in the air at different temperature, that is good enough. And here is the formula. Okay, and in this chapter, mainly I would like to focus the Doppler effect. Doppler effect. Okay, if the source of sound and the observer, they are in relative motion, then we can observe the Doppler effect. The frequency changing, frequency shifting, that is what we call the Doppler effect. For example, let us suppose this is the source of sound. Whatever, like you can say amplifier, whistle, radio, whatever, but this is the source of sound. This produces the sound wave. An observer is right there. He is an observer. He hears the sound coming from this source of sound. So this is source of sound, this is observer. And I already mentioned that the sound wave needs the medium to propagate. And simply we consider in between this source of sound and the observer, let us consider there is a air. But we ignore the motion of the air here, okay? We do not consider the speed of the air. We simply consider the speed of the source of sound and the speed of an observer, okay? So if there is a relative motion between the source of sound and the observer, we can observe the Doppler effect. That means if the source of sound is moving or if the observer is moving, or if both of them they are moving, then in that case we can observe the Doppler effect. Okay. So if both observer and the source of sound they are at rest, stationary, no Doppler effect. Okay, if source of sound is at rest and the observer is at rest, and let us suppose the sound produced from here, and let us consider f0 is the true frequency of sound wave. If f of 0 is the true frequency of the sound wave, and if the source of sound and observer they are at rest, okay, the sound is coming from here, and this observer hears the sound wave, and the frequency heard by this observer is same as f0, no change, same frequency, we call this is the true frequency. Again, if the observer and the source of sound both are at rest, the observer hears the true frequency. So you can make this, this is the first case, source and observer both are at rest. Case 1, source of sound and observer are at rest. So in this case, observer hears the true frequency. There is no change, there is no shift in the frequency, no frequency shifting here. Okay. So now let me draw the diagram again. Okay, so here consider this is the source of sound, and here is the observer, this is observer. So I already told you that f of 0, let me call this is true frequency of sound, and the second, this is also the frequency, but this is the frequency observed by the observer, so you can say observed frequency. This is the frequency heard by the observer. Let us suppose v, this is the speed of the sound wave in air. V is the speed of the sound wave in the air. I told you that we ignore the motion of the air. This V, this is the speed of the sound wave, not the air. The speed of the sound wave in the air, and which is at room temperature 343 meter per second. So if you have to solve the numerical problem, you can use this speed 343 meter per second. This is at room temperature at 20 degrees Celsius. At 20 degrees Celsius, I consider 20 degrees Celsius is the room temperature. If you have to figure out the speed at different temperature, I already gave you the formula. The formula is V equal to 331 plus 0.6 times temperature. This is in meter per second. If you want to calculate the speed at different temperature, plug the temperature right here. 10 degree, 15 degree, 20 degree, 25 degree, whatever. You can get the speed. Okay. So this V is the speed of the sound wave in the air. And V0, this is the speed of an observer, and Vs, this is the speed of source of sound. Now there are the 4 cases. One, I already mentioned that if the observer and the source of sound, if they are at rest, no Doppler effect. So in that case, simply you can write down frequency observed by the observer, f, this is equal to f of 0. That is the case if the source and observer both are at rest. Both at rest. Observer and source of sound both are at rest. If the source of sound and observer both are at rest, then in that case the observed frequency is equal to the true frequency. Okay, then another case I want to call, so here please don't forget these parameters here. Okay, so another case is, let us suppose the source is at rest and observer is moving toward the source of sound, but source of sound is at rest. Okay, source of sound is at rest. Let us suppose somewhere there is a source of sound and I am walking, I am the observer and I am walking toward the stationary source. So that is the first case. Okay, let me make that. If you want to consider this is the first case, then you have to say second one. So, but I don't think this is too simple, so I don't think I have to make this case number 1. It's up to you. Okay. Now my first case is, this is observer. Observer, he is moving toward the source of sound. So V sub O is certain speed, like a 10 meter per second. 10 meter per second, that is to be. So whatever speed is given. Okay. This is V0. This is the speed of an observer. And in this case, I want to consider Vs. This is the speed of the source of sound, but I want to keep this at rest. So Vs is equal to 0. So the case number 1 is observer is moving toward the stationary source of sound. That means V sub S, this is equal to 0. So what happened? What do you think? If this observer is moving toward the stationary source, what happened? In this case, observer hears the more frequency, bigger frequency, more than the true frequency. So in this case, observer hears more. Observer hears the frequency more than true frequency. And the frequency observed by the observer, because observed frequency is f, this is equal to f of 0. This is the formula to calculate the observed frequency. F of 0 is the true frequency. V, speed of the sound wave in the air, plus V sub 0, this is the speed of an observer, divided by V. This is the formula to calculate the frequency, observed frequency, if the observer is moving toward the stationary source of sound, and let it be equation number 1. So this is the case if the observer is moving toward the stationary source. And the second case, in this case, observer moving toward the stationary source. Okay. The second case is, you can make this, if the observer is moving away from the stationary source, like this. Okay. So the second case is, source is still at rest, but the observer is moving away from the stationary source. So the second case is, observer is moving away from the stationary source. Observer is moving away from the stationary source. Now what do you think in this case what happened? In the previous case, observer, he was moving toward the stationary source. Now the observer is moving away from the stationary source. In this case, the observer hears the less frequency. Okay. In this case, observer hears less frequency. Okay. And the frequency observed by the observer f, this is equal to f of 0. In the previous case it was v plus v0, because that was the bigger frequency. In this case it's smaller frequency, so you have to write down v minus v sub 0 divided by v. This is the second case. Okay, so in this case, the frequency observed by the observer is less than the true frequency of the source of sound. I mean the sound wave, less than the frequency of the sound wave. So this is equation number 2. Okay, so here we keep the source of sound at rest and the observer is moving toward the source of sound, first case, and the second case, the observer is moving away from the source of sound. Now, let us keep the observer at rest. This is your second case. Now, the third case, let us keep the observer at rest. What happens? Let's see. So, I want to keep the observer at rest. That means V sub O, this is equal to 0. Observer is at rest, stationary. Now the source of sound is moving. Let me call this is V sub S, source of sound. So the third case is the source of sound is moving toward the stationary observer. That means V sub O, this is equal to 0. Okay. So what happened in this case? So the source of sound is moving toward the stationary observer. In this case also, the observer hears the frequency more than the true frequency. So in this case, observer hears the frequency of the sound wave coming from this source. So the frequency of the sound wave coming from this source, the observer hears that, and that frequency is more than the true frequency. So you can write down in this case the observer hears the frequency more than the true frequency. That means the observed frequency is bigger than this. Observed frequency f is bigger than f of 0. This is what happened. So what is observed frequency then? How do we calculate that? The formula is f observed frequency. This is equal to f of 0. V divide this by V minus Vs. This negative sign, because we need a smaller number here in the denominator so that we can get the bigger f. That is why I put the negative sign there. So this V is speed of the sound wave in the air, 343 meter per second. Same thing, this V and this V, they are the same. Vs is speed of the source of sound which is given. Either given or you have to calculate. Okay. So this is the case if the source of sound is moving toward the stationary observer. In this case, the observed frequency is more than the true frequency, and this is the formula here. Okay, and let me call this is equation number 3. Third case, and the fourth case is again I want to keep the observer at rest, but the source of sound is moving away from the stationary observer this way. Okay, this is the case number 4. Case number 4 is the source of sound is moving away from the stationary observer. Number 4, the source of sound is moving away from the stationary observer. What do you think? What happened in this case? So here is the observer, source is moving away from the observer. That means you can think about, later suppose you are standing on the train station platform there. You are standing there and the train passes you. Train is moving away from you, not approaching, to go away from you. So you are at rest, The train, it produced some kind of sound. The train is moving away from you. What happened in that case? What frequency do you hear? You hear the frequency less than the true frequency. So you can write down in this case, the observer hears the frequency less than the true frequency. Less than the true frequency. That means F, observed frequency, is less than true frequency. So how do you write down the formula then? This is observed frequency, this is true frequency. I need this number is smaller. So you put plus sign here then. Okay, this is observed frequency, this is true frequency, this is the speed of the sound wave in the air. Same thing, speed of the sound wave in the air. And this is the speed of the source of sound. And this is case number 4. That's all. We have 4 different cases. So let me summarize. If the source of sound and observer both, if they are at rest, then in that case you have the observed frequency is equal to true frequency. This is the case if the observer and source of sound both are at rest. Another one is if the observer is moving toward the stationary source, your formula was F equal to F of 0 V plus V0 divided by V. This is your equation number 1. This is not new equation, I already told about it. Equation number 2, observer is moving away from the source of sound. So in that case, observer hear less frequency. So you can write down F equal to F of 0 V minus V0 divided by V. This is the second equation. Okay. And third case, the observer is at rest. The source is moving toward the observer. More frequency in this case. The observer observes more frequency. If the source of sound is moving toward the stationary observer, in that case, observer observes more frequency. So you can write down F, the observed frequency. This is equal to F of 0 V, divide this by V minus Vs. No observer is speed because that is 0, and here Vs is the speed of the source of sound, which is your equation number 3. And the last one was the source of sound is moving away from this, moving away from the observer, and in this case observer hears less frequency, observer observes less frequency. So you can write down F equal to F of 0 times V, divide this by V plus Vs. So this is your equation number 4. Okay. So look at these 4 equations, 4 cases. This is observer moving toward the stationary source, equation number 1. Equation number 2, observer moving away from the stationary source. Equation number 3, source of sound is moving toward the stationary observer. Equation number 4, source of sound is moving away from the stationary observer. You don't have to remember all these 4 equations. You can combine them together. You can write down like this. Your observed frequency F, this is equal to F of 0, this is true frequency, times V plus or minus V0 divided by V minus or plus Vs. Just this equation is good enough. This equation is good enough. Now, how do you use this equation is, if you choose the plus sign from numerator, if you choose plus sign from numerator, choose the minus sign from denominator. For example, if both observer and source of sound is moving, and if you have to choose plus sign from numerator, please choose the negative sign, minus sign from denominator. If you choose minus sign from numerator, choose the plus sign from denominator. So if you memorize this equation, you can get any equation. These 4 equations. For example, if the source of sound is at rest, if the source of sound is at rest, so this term is 0, Vs is 0. So you don't need this term. So you go here, Vs is 0. Here you have a Vs, but if Vs is 0, then you don't have to write down this. Okay, that's the first thing. The second is, okay, the source of sound is at rest, so this becomes 0. Now you have to choose either plus or minus here, right there. You have to choose plus or minus. How? If the observer is moving toward the stationary source, you hear the bigger frequency. To get the bigger frequency, write down the plus sign. Then you get the equation number 1. So from here, from this equation, you can get this equation. Second case, again, the observer is moving away from the source and the source is at rest. So again, this is 0. That is why you do not have a Vs here. Nothing, no Vs, because this is 0. Observer is moving away from the source. You hear the less frequency. Observer hears the less frequency. To get the less frequency, you have to put the minus sign here. So look, from here also you can get the same equation. V minus V0 divided by V. Of course, you have to multiply by f of 0. So you can use this equation to get these equations. So again, please note, we can observe the Doppler effect if there is a relative motion between the source of sound and the observer. And as needed, we can calculate the frequency, we can calculate any parameters. Okay, here we have, you know how many? F of 0, F, V, V0 and Vs. 5, right? So if 4 of them are given, then of course you can find the 5th one. Now people, they can ask you, let us suppose you are driving and you are playing the music like a CD player. In your car, you are driving like 70 miles per hour. Do you observe the Doppler effect there? Because you are playing the music, you hear the sound and you are driving. Do you? You don't, because both you and the sound, the source of sound, they are moving in the same direction, same speed, everything is same. You do not observe Doppler effect there. But let us suppose you are on the right lane and someone is on the left lane. You are driving this direction and the other driver, he is driving the opposite direction and he is playing the music. So you move this direction, the other driver moving in the opposite direction and playing the music. You observe the Doppler effect there. Okay, you are observer moving this direction and the source of sound, the other driver who play the music coming from the other car, that is the source of sound, and he is also moving. You are moving to this direction, let us call this is to the right, and other driver moving this direction, which is the source of sound, and to the left, the source is moving, observer is moving, you observe the Doppler effect. Okay, so this is all about the Doppler effect. Okay, so again, it is about the sound wave, but the Doppler effect you can observe in light wave also. Every wave they show the Doppler effect, but the Doppler effect is kind of important in sound wave. That's why we did it here. Okay, so this is all about the Doppler effect. Thank you.